Okay. Right. So today, we're going to sort of look at one very useful, but quite straightforward approach that you might be interested in applying to a sort of simulator, and we'll sort of show how you make it faster through emulation, and that's sensitivity analysis. So this is sort of taken from Chapter 1 of Saltelli. A possible definition of sensitivity analysis is the following: the study of how uncertainty in the output of a model, numerical or otherwise, can be apportioned to different sources of uncertainty in the model input. A related practice is uncertainty analysis, which focuses on quantifying uncertainty in model output. Ideally, uncertainty and sensitivity analysis should be run in tandem, with uncertainty analysis preceding in current practice. So if you think about the example that we were talking about in terms of climate modeling and saying, well, we've got real problems in understanding the quality of our ability to assess the amount of ice dropping into the Southern Ocean, a sensitivity analysis might be, well, looking at the overall climate and sort of saying, well, how sensitive are our future projections about the climate of some form to that input variable? Because if it turns out that actually the projections are the same, then we don't have to spend ages fixing up the ice sheet model. Now, I'm no expert, but I suspect that it's probably pretty sensitive to how much fresh water is entering the Southern Ocean. But that's the sort of question you might want to answer. How sensitive is it? So the study of how output uncertainty relates to input uncertainty, and that determines which inputs contribute most to output variations, and is a complement to sub-uncertainty analysis. So there's a sort of notion of best practice that is suggested in that quote, that is run the uncertainty analysis first, then sensitivity analysis. And just to split two things. So one can imagine two types of this type of sensitivity analysis, which we'll think of as local sensitivity analysis and global sensitivity analysis. We're going to focus actually on global sensitivity analysis today. But local sensitivity analysis, in some sense, it's somewhat simpler and conceptually easier to think about. So local sensitivity analysis would be that you look at the operating points of your model. So, and then you take the gradient of that model, so partial derivatives of the model with respect to the inputs you're interested in. So that gives you a Jacobian matrix, and that allows you to linearize around that operating point, right? So in that situation, what you're doing is you've got some simulation that if we were to look at the emulation, it might be a function like this. And what you do is you linearize at the point of operation. This used to come up a lot in Amazon, where there would be some projection of what you expect the stock to be based on the inputs, which are around supply and demand and how you're distributing your resources. And then you might find what they would call in supply chain a variance, but what we would call in statistics and machine learning a residual. Yes, thank you. Yeah. I don't know why this opens up in a sort of zoomed in way, a residual. Right? So a residual being the difference between the anticipated output and the expected. We would say the variance is the sum of the squares of the residual, right? But in many fields, when they're talking about variance, they're talking about the variance between the prediction, and so this is where you get these confusions between related subfields. So I don't know where that's coming from, if that's coming from the OR community or the economics community, because the supply chain teams I was with had a mix of all these people, but we would think of it as a residual. And so you've made this prediction that you're expecting to see that you have a certain amount of stock, and you don't. And so then they would say, oh, I want to explain the variance, I want to explain the residual. And what they would often do is they would say, well, we were operating at this point, where this point might be a sort of a certain stock, that there's 50,000 items in stock and some other parameters around the point of operation when we made the decision. And then you might try and linearize around that operating point, and then use that linearization to explain when it came to, and it's often the residual you're trying to predict, trying to explain what that residual is due to. And the sort of answers you might get is, oh, it's because supply came in under what we expected, right? So our expectations were supply was going to be in this range, but the supply was down on that, and that's why we're out of stock. Or it might be, oh, because demand had a spike that we didn't anticipate. So this spike in demand means we're out of stock. And that's the sort of answer that the vice president's looking for, so that they know what intervention to make, because these would be automated decisions that had been made from the previous week's algorithms, and they were asking these questions to understand. They had a special term for it that I can't remember the name of the term, but it's sort of like interventions that they needed to take to fix the system before this got any worse. Well, I can't remember what they used to have. Oh, do we need to do any? It's like, it wasn't rectifications, but a term like that. That the human wanted to come in on. And so that's like a local sensitivity analysis in some sense, because, or that's a localized analysis. And then you're understanding how these things are all varying within the scope of a local area, right? Because you're looking at a local linearization. Now, the difference between that and what we're going to be talking about today is a global sensitivity analysis. You look at the whole range of inputs, right? So you define your total input range and sort of say, what's going to happen over this entire range. So we're sort of thinking about, you know, the plausible range of inputs and how are the outputs varying. So you can see those two are sort of slightly different. This one's operating through gradients and linearization within a local regime, which will be valid. This one needs to do an integration over the whole thing. I mean, effectively, this one is almost like having a sort of small delta function in that region there as the sensitivity. You can think about it that way, whereas we're actually going to integrate in a sort of full uniform distribution, or whatever the appropriate distribution is of expected inputs to the system. So this is working for today and what happened last week, but this would be, well, this is what the system would do overall, or how it would vary. So different types of questions with different types of analysis. That makes sense? So we're going to focus on, in the course, the global analysis. So that sort of involves sensitivity analysis across the entire input domain. And what we're going to use is what you could refer to as ANOVA, an analysis of variance, for what of the inputs are affecting that output variance. So what we're going to do is we're going to look at how that function is varying across the valid input domain, and then we're going to try and decompose that variation into the different component parts, which are sort of individual inputs, like in climate, again, how much fresh water will enter the Southern Ocean, or I don't know how much, what the carbon dioxide trajectory will look like, some other large-scale inputs. So the individual influence of those, but then the very cool thing about these the Sobel approach is you also start looking at coupled inputs. So if it was just a linear sum of inputs, a linear model would be roughly appropriate. But in these nonlinear systems, there's couplings. There's things happening where two things might have an effect together, even though each individual thing isn't having an effect on its own. And what the Hoeffding-Sobel decomposition, this analysis of variance, does for us is it allows us to decompose that output signal into these interacting terms as well, so that we get a sense of, okay, while the amount of fresh water entering the Southern Ocean is not important, it becomes very important on its own. It becomes somehow very important, perhaps, if we consider its correlation with, I don't know, the amount of algae generation in some area, right? That those are the two factors. So that suddenly gives you an ability to say, oh, maybe we should intervene on the algae, or whatever your conclusion is going to be. Please do not take any climate advice from me in terms of geoengineering. Okay, so the math is sort of as follows. So let's assume that our simulator is some sort of function g of x. That's what's coming out of the climate simulation. And our domain of inputs is p of x. So these are inputs that we think of as valid things that are possible to happen. And then what I'm writing here is the total variance of the system. And if the total variance is, in the notation I use for expectation, which is a notation that comes from physics, so all these angle brackets mean is just expectation of this function under this distribution p of x, as defined below. That's all that's saying, right? This is the expectation. Sometimes people use an E notation for expectation, but I like this notation because it makes it clear what the expectation is under. And these it's a sort of, you can also see what's being calculated. So this is the total variance because it's the expectation of the square of the distribution minus the squared expectation of the function, sorry, the square of the function minus the square of the expectation of the function. So this is the mean of the function, right? And that's the expectation of the square. So you subtract the mean squared off the expectation of the square, you get the total variance. Now, what we'll do for the work we're doing here is we'll make a few assumptions which can all be modified in practice, but let's just assume that the inputs are independent, that there's not correlation between how we're going to vary them. In practice, that might not be the case. And we'll also assume each input is uniformly distributed. So it's going to be across some interval that will just scale to be 0 and 1. We can do that without loss of generality. In practice, you might have to think a little bit more carefully about this distribution of inputs. It could be that one of them is distributed according to a Gaussian or a mixture of Gaussians, whatever one thinks is appropriate. You would need to know the right answer to that depending on the context of the problem that you were simulating. So that, in effect, means that this is our assumption about our input distribution, right? Okay, so now what we're going to look at is the Hoeffding-Sobel distribution. So this is a decomposition, which I kind of think of as an ANOVA decomposition, that says that this function, g of x, can be decomposed into the following components. One, which is a constant, g0, that is not dependent on any of the variables. Then a sum of terms where each term is dependent on one of the variables. So you take a constant, and then this second piece here is just saying add to that constant, if there's p inputs, a sum of univariate functions where each of these functions, notice I've indexed them, so they're different from this g, they're all sort of indexed. Each of these functions is a function of only one variable, right? So in our climate example, one of those functions would just be a function of the amount of fresh water entering the Southern Ocean. Another function could be just a function just of some profile of the carbon dioxide rise, right? That's term one. Then term two is another function that is only dependent on two of those terms, right? So this function could be a function of both the water entering the Southern Ocean and the carbon dioxide rise. But it's being added, it's only going to take care of a residual. So think about it in this way. You can sometimes think of it in residuals. If we put the g0 on the other side, so g of x minus g0 says, oh, you guys are going to have to take care of the residual after we've taken the mean off, right? So now mentally think about, oh, what if I then move this onto the other side? G of x minus g of 0 minus the sum of these things. This function is now required only to mop up the piece of the explanation that doesn't come from these univariate functions. It's just like, let's do all the bivariate things, right? And then you keep going. So this is the trivariate contributions. And then all the way up to the contribution, the one contribution that will come from the residual that you have to consider every single variable in order to predict. Now, if there's any sort of structure in the problem, as you might expect, this decomposition will likely have some of these terms, these functions that are quite small. And that's kind of what you're looking to explore. So actually, oh, goodness, I'm not sure if I've mentioned this yet. One of my favorite videos of the year is watching Terence Tao talk about the use of AI in maths at the International Maths Olympiad. It's about an hour long. It's a talk he gives. I think it really, to me, captures the essence of what we're trying to do in ML in the physical world. He's talking about maths, so everything he cares about is about creating mathematical proofs that are beyond the scope of any individual human to understand the whole of, but that we can use computers to prove that they're true through proving languages and supporting humans in creating such proofs through verification techniques, proofing languages, and LLMs to help you understand where you need attention or to support you in your attention. So I was mentioning that for a point, and now I'm going to have to reverse and try and remember because I got over-enthused with the talk. So in that, one of the things he talks about machine learning being useful for is data-driven analysis of mathematical tendencies. So you take some known math, and this is something that Challenger Mishra works on in this department. So you take some mathematical conjecture and you generate data that you know fulfills that conjecture. And then you fit a machine learning model to that conjecture. But then you analyze that machine learning model with this sensitivity analysis. And perhaps it says, this has been done in knotting problems, I think. So in knotting problems, it may then say, oh, you thought that this mathematical result could be the packing problem as well. This mathematical result was dependent on these 7 things, and you kept trying to find proofs that involve these 7 things. But our data analysis, our sensitivity analysis of this system shows that only these 3 terms and these 2 coupling terms are having an effect statistically. Perhaps you should go and look for proofs that decouple in that way. Beautiful, isn't it, right? And then you go and prove it and go, oh my goodness, of course, if I can ignore that term, I can show that it's an elliptic continuity curve in something that a pure mathematician understands. I'm just making up words, right? But that is the sort of thing that he mentions in the talk, and the sort of things that we're seeing machine learning being used in pure maths for, right? Which I just think is like, you know, extraordinary. If I told myself that, if I tell myself from 15 years ago, oh yeah, Terence Tao will be talking about that, you know, to me that would have just seemed, oh wow. So no sort of like, you know, it's not like the AI is working out the pure maths. No. Techniques like emulation and sensitivity analysis can be used to unpick things that are harder for humans to see in large-scale data sets. So what we end up with when we're doing that is we end up with this constant term, a set of individual effects, and then a set of interaction effects. So second order followed by higher order. Now, typically, because, you know, there's a bit of a challenge if it turns out that everything's involved, as it is in some systems, right? This doesn't help you very much. But the sort of hope is that you're going to get some sort of sparser representation in this. And this is what the analysis tells you. So, oh, that's, sorry, let me just see if I can zoom out to pick in the last term there. Right. So what we can show mathematically is that the constant term is simply given by the expectation of the function, right? So what we can do is we first of all calculate the expectation of the function. And then through that process of back substituting G0 onto the other side, we can then start decomposing each of the other terms in, sorry, I forgot to put the screen back on. Each of the other terms in the following recursive way, that we now look at the individual effects as the expectation of each function. And notice this notation here. This is an expectation of the function under the whole of the distribution over X. What I mean by this notation here is an expectation under every variable apart from the ith one. So this expectation, because it's an integral over the whole X, obviously results in something that it doesn't depend on X anymore. Whereas this expectation is integrate out all of the other variables apart from the variable of interest on this left-hand side and subtract that. And you just keep going through this process. So to get the next, so you're effectively looking at residuals, right? You're taking this piece off the main function. You're looking at the residual of the summing function to get the, from here, to get the individual effects. And then you just repeat that process. So every time you develop one of these, you go through it to do the first order effects, and then you have to do the same thing to do the second order effects. Now, what's the problem going to be with this approach? So these expectations, this is a high dimensional integral. If you've got 1,000 inputs, you're taking an expectation over a high dimensional integral, and you're just going to get a function of one thing out. So in order to take that expectation, we can't integrate directly. We're going to have to use sampling. And if that's a high dimensional, that could be quite intensive sampling. And for every single one of these samples, we have to run the simulator. Or do we? because of course the story is that we'll try and build an emulator that means it's quicker, right? Build an emulator, try and approximate the function, and then run on the emulator rather than the simulator to try and approximate the sensitivity analysis. Does that make sense? The other problem is that every time we do this, to get the next higher order effects, we have to do it again, right? So if I want the second order effect, I have to first of all do the first order effect, and then I have to do the second order effect. And to get the second order effects, how many terms am I going to have to be subtracting off? Well, I'm going to have to do the integral over all these combination things. So it gets a bit more complicated as I go forward. So to get the two-way introductions, you see, I have to do this, right? And then I'm recursively having to do this all the way through. Sorry, that bracket indicates that's a bit of an error. That shouldn't be appearing on the slide. It's in the notes. Apologies. Just pay attention to the first bit there. And I have to keep doing that recursively. Right. So what this leads to, if we then normalize by the variance, is what the so-called Sobel coefficients, that we end up decomposing, because we can remember that decomposition. Let's go back to that decomposition again. Now, the beautiful thing about this is by decomposing in this way, this way, this is what gives us an analysis of variance, right? So what we can now see is, because what we're saying is the function on the left is the sum of a number of functions, the variance of the function on the left is going to be the sum of the variances of the function on the right, right? Because variance is sum in that way. So if we then want to know what the contribution of each of these terms is, if we divide by the total variance, each of these variance terms, we get an index, and these are called the Sobel indices. And they're telling you the percentage of the function output that is dependent on that variable. So extremely interpretable. You're sort of ending up with an index that says 5% is dependent on this one. That's what this slide here is saying, right? There's also, so Nicolas, he's in the Cambridge ecosystem. He used to work up with me in Sheffield. And before he worked with me in Sheffield, he worked with Tony O'Hagan and others in Sheffield. And he's just brilliant on a lot of these. And he works for a company now that would love to employ many of you when you graduate. Whose name I forget at the moment. All companies have weird names now, don't they? Like Clumbo or Brimba or something like that, you know. So a very interesting company that is building electric motors and using emulation techniques to refine and improve the quality of electric motors, design better electric motors. I'm not sure whether we've got them up, but last year he gave a guest lecture on how that's being done and how they're using emulation. But he has a whole history in the theory of this stuff and some very elegant papers, including one where Nicolas actually introduces these notions of analysis of variance. This was, I think, something he had originally started in his PhD work, into kernel representations. So a notion of an ANOVA kernel. So you actually decompose this in the kernel within the Gaussian process. That's not what we're going to do today, but it's a beautiful piece of work. So the Sobel indices, right, they now tell us what we're doing is we're now decomposing the function into these parts, what percentage of the total variance we're getting. And the Sobel index we get is a sum of these indices where we're getting individual inputs, S1, pairs of inputs, S12, S23, S13, etc., and then higher order interactions. And then you know that the sum of these whole things will sum to 1. Now, in practice, we don't normally compute all of these indices, because for like an 8-dimensional input, the amount of work you have to go through to actually compute all of these becomes too many. You might just look at first order interactions and second order interactions, right? But the nice thing is you get the indices for them and you can see what the residual is, right? So you're saying, well, I've done first order and second order, and that's giving me like 87% of the variation. There's 13% of the variation is going on in higher order interactions. So you're not necessarily obliged to work out the whole thing, which sort of makes, you know, but you can just check out the sort of univariate and the bivariate. So the example in the notes is the Ishigama function. And the Ishigami function is a test function that's useful because we can actually compute all these Sobel indices analytically in this case. It just happens, it's chosen for that reason, right? There's some interesting interactions. I'll show you the function in a moment. But don't get confused. We wouldn't normally expect to compute these analytically. We would normally expect the Ishigami function to be replaced by a climate simulation or something very complicated. And what we're going to do in this little walkthrough is we'll demonstrate exact calculation for the Ishigami, and then we'll go to Monte Carlo simulation that allows us to extract and estimate these things just by sampling. And of course, this is a very cheap function to compute, so we can easily do Monte Carlo estimation. And then we'll show what happens when you do the GP emulation. And in the GP emulation, what we're also going to be doing is using the acquisition functions that we talked about on Tuesday in order to approximate the simulation, right? So uncertainty sampling or integrated variance reduction. So here's the Ishigami function. And what's interesting about it is it has sort of an interesting nonlinear interaction between x3 and x1, right? So it's a function of x1, function of x2, and then a function of a combination between x3 and x1 in this sort of interesting way. And this is what it looks like plotted from x3 to x1. So these are the sort of three things that are being summed together. x1 and x3, this sort of function, and x1 and x2, this sort of function. Yep. And it just happens that we can integrate that. You know, I'm not going to go through the details of that. Oh, sorry, I've somehow should have had a new slide in here. So let me go to, see if I can go to, I did try earlier and run, and this is where we test if the, okay, it looks like this is actually all run. This is the notebook for today. Oh, why is that not showing up? Oh, no, computer says no. Let's try and zoom in. This is where we're at. Okay, we just got to there, right? So the total variance, in what you can, well, let's make sure we've got the setup upset, because this is all being done in EmuKit, right? Target simulator is all being set up here. And these are for some plotting some functions of it. So these are all setups in EmuKit because the Ishigami function is implemented in EmuKit for this example. So from EmuKit test function sensitivity import Ishigami, right? So we're getting the Ishigami here. Now in EmuKit, what we're doing is we're importing parameter spaces in the notion of continuous parameters. So what's that all about? Well, we're going to search this function continuously, right? It could be that it's a discrete function, right? So we could be interested in functions where there's some discrete change. And in that case, the acquisition process is different, right? The optimization process of the acquisition function is different. So you're specifying that you're working with a continuous parameter space here. Here, you're giving the variable domain. So you're saying, I'm interested in the parameter between minus pi and plus pi. With that variable domain, specifying the overall parameter space. And now here we're using that variable domain to create a grid just for that plotting that you just saw, right? So this is just all plotting functionality to give us those outputs. That appears twice, by the way, because once is the one generated from that code. So when you open this stuff up, you won't see that plot. You have to run the code to run that. And then we've got the total variance in this. It's known, we can compute it. That's what the total variance is. So that's the sum of the variances of how this thing is working with G1, G2, and G1, 3, because there are no other components. There's no component of G3 on its own, and there's no interaction between G2 and G1 or G2 and G3, right? So that's the full specification, and there's no three-way interactions. And so we can compute these analytically, so they're given here in this way, but now we're going to do them using Monte Carlo, right? So in general, these indices, in most cases, are interested in first order. Ishigami has a benefit; these can be computed analytically, but in EmuKit, you can extract values with the code main effects. But in general, these indices need to be sampled with Monte Carlo or one of the quasi-Monte Carlo methods we've seen in the model-free experimental design, previous lecture. With EmuKit, first Sobold indices can be easily computed. We need to first find the space where the target simulator is analyzed. So Monte Carlo, import model-free Monte Carlo sensitivity, random seed. How many points of Monte Carlo do you want to do? And then off you go. And now we've got just in this, the target simulator and the space, which is defined above. And then we're getting in the main effects and the total effects, right? And then you're seeing the main effects. So the main effects are the individual variants, etc., of these different functions. And so what we do is we compare them to the ones we see in practice. So because it's Monte Carlo, the third effect is not quite zero. But the other two, you can see the slight error between the truth and the Monte Carlo estimate. Now, that's computed with, what do we say? 10,000 samples, right? So that's quite a lot of samples. If we were to drop it down to, let's see, run before. It's so awkward doing this in notebooks. It'd probably take half an hour to now do that. But what I was just thinking of doing is just showing how bad that gets if we drop it down to like 100. Let's see that getting worse. It might take a while for that to do that. We'll scroll back up. But what we're going to do next is this implies that we've run our climate simulator 10,000 times across 3 variables, which is just probably on the UK's Met Office one that we talked about earlier, that would take 30 years or something, you know. Maybe not 30 years, but 3 years or something. So what we're interested in is, sorry, I forgot to say that also we can then look at the total effects, right? So the nice thing is we can also compute the total effects and therefore find the residual. And there's the analytic computation of the total effect. And then the next piece is sensitive view. Let's go back up the top, see what happens when we drop that, see if that code's run. Oh, still running. Problem is the start of the notebooks, as you've probably seen, the first thing it has to do is make sure all the right software is installed. And when I ran everything above, it will have been reinstalling software potentially. We're all the way up here. Yeah, oh crumbs. It's not even got past there. Something's gone funny. That's still spinning. Oh, I know why. Sorry, because it's some runtime interrupt execution. Sorry, it was waiting on input from some function below, which is why it wasn't rerunning. Let's go back over again. Where were we at? Yeah. Done before. That won't take too long. And then we'll just see, like, when we go down to very low samples, what we'll see is the ability of the Monte Carlo to map on to the truth gets reduced. And that's why we then will turn later on to the process of actually fitting the GP Monte Carlo, which is a 2-stage process. So what we include when we're doing the GP regression we include an MUKIT model. And then when we're doing the MUKIT things, we now include compute effects, GP base. So that's just the somewhere up here, GP regression model wrapper. Oh yeah, so that's just optimizing there, right? So here, this is as simple as it is, right? That this process just goes through the optimization of the model, doing all the relevant data selection. And then this bit of code here is doing the Gaussian process-based implementation. So you see a slight variation between the Gaussian process one and the Ishigama one. But let's go back up now, see if that finished. It's done by now. Where was it? Snowball through. Here we go. I think it's ready, isn't it? Yeah. Okay. And then, so here's the plot. Okay, look how bad it is now, right? So reducing the samples down to 100 to try and get us that better approximation really reduces the quality of the Monte Carlo estimation, because even in three-dimensional space, that's not enough. Now, I can't remember how many we're using down below with the Gaussian process, but basically the idea is, so random design 500, okay, so it's 500 here, right? So let's see what happens if we put, and it may get upset because I've gone back in the order of execution, but let's put 500 in there and see what that gives us. Okay, so that's what it's giving us with 500 samples. And that's what we're going to use to fit the Gaussian process. So we're basically using 500 samples to fit our Gaussian process. And then, which is this piece here. And then once we've got that, we're doing the Gaussian process Monte Carlo. Okay? So it looks like it's better, you know, and the reason it's better, the reason it would be better is because there's additional assumptions in the Gaussian process about how the function is moving between those points, right? If those functions are wrong, by the way, it will be worse, right? So if you choose the wrong covariance function, if you sort of decide, oh, if the actual system is really fluctuating with some large amount of noise, and then you're coming in and sort of smoothing that with a Gaussian process approximation, then you'll find you're worse than the original because you've introduced invalid information. You've introduced bias in the model. So part of the art here is making sure your emulator fits. Okay. And then there's an exercise at the end, which again, this is taken from work Nicola did. So Nicola, he's done a lot of teaching on this. And one of the really cool teaching exercises he used to do was supporting people with training them to improve the design of a paper helicopter. So like you make a paper helicopter and you see how long it takes to fall to the ground, and then you do Bayesian optimization on it. And I thought that was so cool. And I said, oh, do you still do that? And he said, well, actually, it's quite hard because there's so much noise in a process like that. So he actually, instead of that, he built this Shiny app catapult simulator. And so as a worked example, what you can go through on this is the catapult simulator. So what the user function is here, the simulator, is effect a request for the user to fire the catapult, right? So that's all this catapult distance thing is doing. Sets a parameter space, sets a variable domain, and then go through the experimental design process. So what it's telling us to do, and this is starting with a design of experiments, is go to the Shiny app here. I wonder if it's open link in new tab. Oh, you don't want to go return to previous page. We're going to page is trying to send you to. Yes, please. Thank you. So here's Nicolas Shiny app. And in the, oh, why am I not getting the other tab? In the other tab, we're getting asked to set the following things: 0.31, 0.95, 0.86, 0.26. So who's gonna, how are we gonna remember those? I can't even remember 4 numbers anymore. It's something to do with age. You take a picture, thank you. There we go. Modern people. This is why I can't remember things, because of camera phones. Okay, what was the first one, Hattie? 0.31. Am I close to it? I can't actually see very well from the side here.
That's 0.2. That's 0.3.
That's 0.3. So there. And then next one. There.
Yeah.
And then next one. And then this one. 0.26. There, yeah. Roughly. And have I got it on wind or not? Does it say it's windy? Breezy. Okay, so we'll put no wind in. That's just adding Gaussian noise. I did the fire button. No, then it sort of shows the result. Which, if it was on a small screen, I can't actually read what that says. Does that say 128.1? So then you go back to here and you say 128.1. Now, what it's doing behind the scenes is it's now, so this is all this is all the design of experiments, right? So let's just assume so this is the static design. So which if I remember correctly in this case is a Latin hypercube design, where you sort of have you divide into rows and columns, and you have 1 point in each row and column. And I'm just putting in some random numbers here to give it something to play with for the next stage, which will be the active design. So, So now we're going to set up the GPy model, fit to those initial static design points, and train the Gaussian process regression. That's all what's happening there. And these are the parameters of the Gaussian process covariance function that's coming up. So now we're going to go for the MUKit thing. Import the experimental design loop and choose integrated variance reduction as our acquisition function. So it's going to start with that Gaussian process it's fitted and do the design space. Now, for some bizarre reason that I don't quite know, integrated variance reduction goes massively slowly on Google Colab. Doesn't on a notebook being run natively. So that will take a while. It is, of course, slower than uncertainty sampling, because this in itself is sampling over the input domains to try and understand how much variance reduction you'll get from different points. So there's some sampling going on inside this inner loop, but it is not this slow on a natively run notebook. I don't quite know why. Maybe all this explains it. Look at this, goodness. All these things going on. But eventually it will come back and give us a point at which it'd like us to ask about next. Of course, it will be all bogus because I put in a bunch of duff numbers. But that's just to give you a sense of this process we're going through, where in this case, you're manually operating the simulator. I mean, of course, underlying Nicolas' code is some kind of code where this could be done automatically, but it's just a bit of fun for you to sort of see how good a job it does at firing off that catapult. With some, then eventually, after you've gone through that, it will give you a sensitivity analysis of the catapult. So I think Nicolas originally used this example for Bayesian optimization, how far to fire, but actually what you're doing with it here is using it to try and understand the Sobel indices. And I guess this is the first order Sobel indices, yeah, of the catapult firing. And it turns out that this arm stop is a significant parameter. That's giving, according to the model,
Oh, there we go. Took a long time to run that loop. Like I said, if you run it in a notebook natively, it should be a bit quicker, but it's chosen this point now, right? If we were to switch, and do try that, it's really interesting. If you try this with uncertainty sampling, all the first points are at the margins. They're like at the extreme. It says, please select 0, please select 1, right? Here it's selecting right in the middle somewhere. So it really does, I mean, that problem, remember we saw in the uncertainty sampling in the one dimensions that it goes to where the variance is highest at the border either side. That problem gets worse when the dimensions go up because there's now more sides for it to keep going into, and it ends up looking constantly at these edges, even though that's not informing it about the region that we're interested in. It's forming it about things that aren't physically possible in this model. But notice with the integrated variance reduction, yes, one of the spring bindings is gone all the way into one direction, presumably because of the static design that was given didn't have a point in that space. But everything else is sitting broadly in the middle, because that's going to give it the largest reduction in variance. And so therefore, if you do go through this, what you should find is that if you use integrated variance reduction as your acquisition function, even though the painfully slow on the notebook, if you do it on a native Colab, you'll find even though there's a bit of extra computation going on, you get a more accurate version of the answer quicker. So that's why sort of acquisition functions are important in getting these things right. So yeah, and then you get the sensitivity analysis, the arm stop, and let's just go back to see why the arm stop's important. So the arm stop on the catapult is, I think, this thing here, right? So if was it this one? Spring binding, the arm stop. So if I put the arm stop all the other way, and that result there isn't the one that I'm taking from the numbers I just put in. It's one I prepared earlier, right? So it's a valid result, not like everything I just did. So the trajectory now, oh, yeah, more. Yeah. The arm stop is having an enormous effect because it's stopping the arm going to its full trajectory. So it's sort of intuitively sensible now we look at the system that the arm stop should be a really important thing. And in fact, it's allowing us to just see the, oh, that wasn't the arm stop, was it? Let's go back out. Yeah, and you can play with this here. Yeah. So that turns out to be the one where most of the sensitivity is, which, I don't know. If you know a lot about catapults, you may have known that already. But if you didn't know about catapults, or this catapults that are represented well by this simple simulation, then you're learning something about catapults and what areas you need to explore in. Okay, so sort of at the end there, I'll sort of stop and just check if there's any questions on that. The next lecture, which is the sort of last of the formal piece of the course,